I am going to talk about marine heat flow techniques. My name is Florian Neumann. I'm a scientist at the University of Bremen, and for the last couple of years, I dedicated myself to collect marine heat flow data in very different geological settings. And for the last year, I'm now working here at the University of Bremen and to continue the work that has been done here in this place. From Sven, you have already seen that a lot of data comes from the ocean. Unfortunately, not half of it. It's just a little bit less than half of the heat flow data from the Global Heat Flow Database comes from the ocean, although 70% of the Earth's surface is ocean. But we do the best as we can to hopefully in the future pass those numbers from the continental measurements for the heat flow measurements, for the marine heat flow measurements. What I'd like to talk about today is first a little bit about the different probe types we are using, how we make a measurement. Then I'd like to talk very briefly about the ocean drilling, because I see it as also part of ocean heat flow values, even though it's a similar procedure as on the continents. I briefly talk about corrections or perturbations to the heat flow measurements, the marine heat flow measurements, and then I have some examples for the different techniques or the different probe types I have been involved with. There are in my opinion, three types, and there are several variations of that three types. So the first one, and it's the first one they have built, it's the bullet probe. It's a steel tube, and within the steel tube there are temperature sensors, and then the probe measures temperature with depth in the sediment. And we have the Lister probe and the outrigger ones. So both of them can, apart from the temperature measurements in the sediment, they can also measure in situ thermal conductivity measurements. So the Lister or the violin bow type, you have a strength member, so a steel tube, and on the steel tube there is a sensor string mounted, which contains the thermistors or the temperature sensors along the strength member, and these can vary for all three different probe types between 3 to 6 meters. For core barrels they can up to 20 or plus meters. For the outrigger, you have a core barrel, so here's a very nice way to collect cores for other studies and also do some temperature measurements on the side. On the next slide, you can see some pictures of the different probes. On the left side, this is an older picture. I got this from Scripps. I think it's Bullard and his team at Scripps Institution of Oceanography in San Diego, where they used the bullet probe type to get the first measurements at sea. As you can see, for the bullet probe, it's really difficult, or it was very difficult to get some measurements, because once you hit the hard ground, the probe started to bend. And to avoid this, the later construction was then the Lister or violin bow probe type, where you have the strength member that helps the sensor string penetrate easier the sediment. The principle, again, is similar, where you measure temperature, and in addition to the temperature, you measure the thermal conductivity. Here you see one of those probes on board. A Mexican research vessel, where you have the strength member, the sensor string, then you have the steel tubes, and within the steel tubes you have power supply, you have the data acquisition unit, so where all the data is stored and recorded. And well, again, this is also not just for the electronics, it's also for getting more weight to the probe, so because the probes are penetrating by gravity. And on the right side, This is an example of an outrigger probe system where you can have different probes, a long probe, or you have those smaller MTLs, those miniature temperature loggers. They record, for the temperature loggers, they record only temperature. For the long probes, there are two different types. There's one where you can just log temperature, and at the same time for the other ones you can do temperature and also in situ thermal conductivity measurements. The newest one, built for the US heat flow program, so Robert Harris, Andy Fisher, and others are built this probe like 2 or 3 years ago, and it's then the state of the art of a new violin type heat flow probe. Functionalities are it's the same. What's new are it's then they use a digital thermistors, and what's also new is that they transmit part of their data through USBL, so ultra short baseline acoustic signal, to have online data. Part of the data is online transmitted to the ship, so you can access very quick the quality of your measurement, so you can see how the probe is situated in the sediment, if it's vertical or the probe fell over and did not penetrate. You can also very quick see how deep the probe penetrated, depending on the semisters within the sediment. And then you can decide if you want to retrieve the probe, if you wire a little bit more in, and then you move to another position to make a new measurements. Because of other probes, they don't have online views of the data, and then you are, let's say, you are blind at the seafloor. So you make a set of measurements, and then you retrieve the probe onto the ship, and then you download the data, and then you can see the data, and then you don't know how much data you collected during your survey. So this is a really nice advantage what the US heat flow program has built. How is a measurement made? So this is a typical plot, let's say, for us marine heat flow scientists. On the y-axis you have the temperature, on the x-axis you have time, and each of those nice colored graphs is one thermistor. On the right side you can see a schematic where the first thermistor is the lowest most thermistor, and the 22nd, and in this case they can be more, they can be less, is the uppermost thermistors. And you can see this also here. So the deepest is the upper one, and the shallow ones is the lower one. And so what's going to happen here? So first the probe is lowered to the seafloor or above the seafloor. In our case, usually it's 100 meters above seafloor, so it's here. And then we let it not free fall, but the winch max speed penetrate the sediment. So this is usually 1.2 seconds per meter. Then the probe penetrates the sediment. There's an increase in temperature due to the friction of the probe with the sediment. Then we wait 7 to 10 minutes to let this frictional heat dissipate. And after the 10 minutes or 7 minutes, a calibrated heat pulse is fired. As you can see here, the spike in temperature goes up from the heat pulse, so the sediment is heated up, and it then decays over time. And this usually takes then also 10 to 15, or depending on the sediment properties, longer. And then the probe is then retrieved from the sediment. If there is no in situ thermal conductivity measurements, then you only have the first part here, where from the frictional heating, the thermal gradient or the in situ temperatures then are estimated. So operation modes, we usually operate in a pogo style, so it means we do several measurements in one row or over a span of time. On the German research vessels, usually we do it at night because there's only, let's say, 2 persons or 3 persons are necessary to do measurements. So one is on the winch and the other one is in the lab, giving the winch operator comments to heave or bring the probe up and down and so on and so forth. And so usually we do this over the night span, so minimum personnel is required. So how is a measurement then be made? So the probe is programmed to start on deck, to start the measurement, and then once it penetrates, a measurement cycle is then started, and one measurement cycle ends if the probe is heaved at a distance from the seafloor. So this can be, let's say here, A3, this is the distance limit, so this would be 30 meters above the seafloor. So now the probe knows there's a new measurement cycle starts here. There is some parameters we can manipulate here, let's say tilt or acceleration. So in this case, this means if I choose a tilt range higher than 10 degrees, 20 degrees, there is no heat pulse fired, because then we know that the probe fell over, the probe is not right in the sediment, so there might be not a good measurement. In order to conserve battery power, then the heat pulse is not fired in this case. And in the plot below, you can see some of those variables coming out from the recorded data. On the first panel, again, you see 3 measurements. This is again temperature. It's all over time. And you can see the characteristic 3 measurements where you have penetration, you have the heat pulse, a decay, the probe comes out from the sediment, and you have some wiggling, some scattered data, because this is the transit from one station to another in the water column. Then you have another measurement, another transit, and then the last part is when the probe comes up through the water column and goes onto deck. The second plot is again time, and then here you have the tilt. So how was the probe situated during measurements and also between the transit. And as you can see, for the measurement, the probe was very, very vertical. So we have a tilt of 1 to 2 degrees. And this is also for the other ones. And also acceleration, so there was no movement during the measurement. If there would have been a movement, then the heat pulse would not have been fired. And pressure is equal to the depth of the measurements. In this case, it's 200 meters. And there's not only the big ones, the heavy ones. So the probe we are using here in Bremen is about 1.8 tons. Other probes are around a ton, depends on the weight stand and so on and so forth. But this is the dimensions you can imagine. But there is also the smaller ones. As you can see it on the right side, these are ROV-based heat flow probes. They can be used as you can see in this picture from the manipulator of the ROV by just stick it in the ground. These are usually between half a meter to a meter, or can also be mounted on the side of an ROV to take some measurements. The measurement procedure is the same. In this case, we only have 5 thermistors. There are some, they have more or they have less, but the principle again is the same, where you have record temperature over time. Okay, so how we get our data, right? Because temperature and time is not gradient or conductivity, none is it heat flow. But again, on the right side, you can see the characteristic plot from our probe, from the different thermistors, and from our first part, from the frictional decay. Using mathematical equations, we get our equilibrium sediment temperatures. So from that part, we can then have a temperature for each sensor over the depth. So the depth is here, the depth or the length of the probe. This is 5.5 meters. And on the x-axis, we have temperature, and then we plot temperature against depth. It's the same for balls. And then we use fitting, and from that, we get the gradient. And in the second part, so decay of the heat pulse, we can then estimate thermal conductivity, because we have the energy we put into the sediment. In the case of the frictional heat, we don't know the energy which goes into the sediment. And from this, again, it's a mathematical relationship, we then can estimate sediment physical properties, in this case thermal conductivity, and then from other relations between thermal conductivity we estimate diffusivity and then can also estimate the heat capacity. So now we have both, and we can do using Fourier's law, or what usually it's been used is just the thermal resistance against the temperature, or also called bullet plot for heat flow, where the regression line is then our heat flow. Then switching from the probe measurements to the ocean drilling measurements, might be a little bit similar for those of you guys who are working in boreholes. So for ocean drilling, there are two different types of temperature sensors are used currently, or they have been using it, because Jordan's resolution program is now over. There is the APCT3 temperature sensor. So this gets into the drilling shoe, so it can be placed in front. And if sediment is drilled, for example, for the Jordan's resolution, they make a stroke of 9.5 meters. So the drilling bit goes to a certain depth, and then the core is shooted into the sediment about 9.5 meters. And at the lowest point, there is a temperature sensors where we get some undisturbed sediment temperatures. That's very nice, because there's no drilling circulation of fluids or so on and so forth. So this is really, really, in my opinion, very good and high quality temperature measurements. And then you can do this over different depth intervals as long as you're in the sediment. If you don't in the sediment, so you have to drill hard rock, then we come back again to those methods are used in continental drilling or continental temperature or heat flow estimation approaches. And there's another one for stiffer sediments. It's called the SET2 sediment temperature probe, and it needs an extra wire line locked down into the borehole and to measure into the sediments. The disadvantage here is that you don't have a stroke of 9.5 meter, so the only depth you measure the temperature into the sediments is just a few centimeters ahead of your bottom hole assembly. These are some examples from a cruise I've been on, and again it's a similar picture what you have seen for the probe measurements. The only thing, there is no conductivity part here in the measurement, so you have a penetration into the sediment, you have some decay of that frictional decrease, and then you have a pull out from the sediment. And this is for different depths, so quickly can also see that temperatures are quite high in this geological setting where we measured the temperature. So for the drilling, it's the same or similar to continental estimates. Then you have to go back to the lab, or you have to have the course on the Jordan's resolution, and then you make some needle probe sediment conductivity measurements. It's important to talk about the perturbations in marine setting. In my opinion, there are four important ones. One is bathymetry effect, so the amplitude of the basement, controlled by the relief, sediment thickness, contrast, or basement conductivity. It's usually for marine settings between 5 to 20%, depending on where you are. It can be steeper features, and the second one would be hydrothermal circulation. This is a difficult one. Also, it's not really, let's say, there is no easy way to correct for that, because fluids take away a huge amount of heat, usually in the early ages of the oceanic lithosphere. And this is for heat flow values we observe and what should be expected for the age of the lithosphere, there is some deficit, and this deficit is then counted for hydrothermal circulation in the oceanic crust. Then the third one is border water and temperature variations. This is a mechanism due to climate oscillations that propagate into the sediment. These are, or this perturbation is particularly important if you measure heat flow in shallow waters, for example, on continental shelves, or if you measure heat flow in lakes. And the biggest, in my experience, is the sedimentation. So because you have high sedimentation accumulation on the seafloor, the background thermal regime needs to get equilibrated with your with the sediments, and this takes some time. So it depends on how fast sediments are accumulated, thermal diffusivity, and how long is this sedimentation process going on. And this can be in a magnitude between 10 up to 50-60%, depending on if you're on in a discharge place of a big river. Then some examples. So this is a setting in the northern Gulf of California. So on the left side you have Baja California. On the north, this is the border between Mexico and the United States. And on the right side you have the Mexican mainland. And here we did a survey. So this is the discharge from the Colorado River. So we have a lot of sediments, up to 7 kilometers of sediments with a really high sedimentation rate. And we made a heat flow profile across this northern basin. It's called the Wagner Basin. And this was made by a 6-meter violin probe. And our results across the basin. So on the lower part you can see a seismic line with the different faults. I don't want to go too much into detail, I just want to explain the different measurement approach. And what we found was that on the left side of the basin there were higher heat flow values, about 220. In the central part of the basin we have a heat flow around 100 milliwatts per meter squared, and on the far right side of the basin we have really scattered measurements and also a mean measurement of about 890 milliwatts per meter squared. Controlled here, the different heat flow values are by some fluid circulation along this major fault called the Wagner fault. So if we cross this fault, there are high values, and we interpreted these values that fluid is coming from the deeper parts of the basin along the faults, and then also redistributed over the smaller faults in the shallower parts of the basin onto the seafloor. And this is why we measure higher heat flow values and also higher scatter in heat flow measurements. In contrast, in the central part, we measure almost consistent values. So this gives us an idea that this might be some kind of background heat flow in this particular basin. Then the other one example is drilling data. So this is also in Mexico, in the Guaymas Basin, is a little bit further south. And what you can see on the left side are the different holes. So each, sites. So each of these are different locations. So they called sites. And within a site, you can have different holes. They are marked by A, B, C, and so on and so forth. I will mute people here because it's. Can I mute them? Mute. Sorry. And yeah, so the numbers are the colors. Sorry, the colors correspond to the different holes and to the different types of thermal conductivity measurements. So for the different units, we made some thermal conductivity measurements with needle probe, a full space, half space, and then back in the lab we measured some samples with the divided bar method. So you have depth on the left side, thermal conductivity you have here, and also the black graph here, the line is the radiogenic heat production. As you can see, it's super low because it's marine sediments. We have some higher radiogenic heat production where we have some inputs from the rivers, from sands, like here in this place, as a little bit higher, but in general, radiogenic heat production is way under the uncertainties of the heat flow measurements. And on the right side, on the upper part, then I present two different things. So in the full circles, this is the usual bullet plot, and the open circles are the temperature depth measurements. So this would be our gradient. So we present them next together, so it's very easy for to compare, and you can quickly see gradients and then the heat flow on both sides. Different symbols reflect the different measurement types. So as I have shown you, the sediment in the deeper for the stroke, so 10 meters up below the bottom hole assembly, and then for the set 2 measurements for the deeper part where the sediments gets a little bit stiffer. And then I think the last example, so this is a survey we did also in Mexico, where we measured very close spaced, so 50 meters across a sill intrusion into the sediments. So this feature is 700 meters in diameter. It's a ring structure. And on the rim of the ring structure, so this is here, you can observe some small vents. You can see some seeping of fluids coming out, and some microbial and also biological flora and fauna can be found close to them. And what we did along 2 seismic lines that were taken in the earlier years, we made a heat flow survey to characterize this thermal anomaly or this thermal feature. And the results were, on the right side, you can see the 2 profiles, so B to B1, so this is the northern part. In the lower part, you can see the seismics, where I outlined in blue the sill intrusion with the highs representing the rims of the sill intrusion, and then in the upper part you can see our heat flow measurements we made. And if you, what we can observe is that once away from this structure, heat flow is usually between 500 or 400 to 550 milliwatts per meter square. And once we approach the rim structure, heat flow increases sharply to a peak of around 3.5 watts per meter square, so 3,500 milliwatts per meter square on the rim structure here of this feature. And in the central part, it's around 1,800. And again, if you approach the other part of the rim structure, then again it increases. And the same picture is for the other perpendicular profile across the structure. So it's a very nice example where we can quickly see there is some non-conductive environment, and it's a very nice technique to measure heat flow across those structures to get some insights of the deeper thermal structure of this tectonic feature. And I think that's for my talk. I would like to point out 2 other marine heat flow talks today. One is from Jeffrey at 3 p.m. GMT, so 4 p.m. Berlin time. And later tonight, Raquel, a colleague from Mexico, is also then talking about more about marine heat flow and its applications. And that's for me. Thank you very much.